There's nothing to do with waiting. You can just get this dynamics. Tell me what you observe at the start of the talk.
There's something strange about it there. Well, if you look at these particles moving,
Yeah.
there's something strange you would notice.
So, hello everyone, welcome to the private seminar. Today we are honored to welcome Bourgade, Professor Paul Bourgade from New York University, Brown Institute. And today he will talk about the stability of non-permission spectra, statistics, and the dynamics.
Thank you very much. So I work at the Courant Institute, which is at Courant, we like to say that there are no mathematicians or applied mathematicians or pure mathematicians, there are only mathematicians. And this being said, I'm more on the theoretical side of random-matrix theory, but I want to mention some phenomena about non-emission random matrices, which I find interesting and maybe potentially for some applied math questions. In fact, non-emission random matrix theory is quite a topic by itself, including in applied math. If you think about the book by Trefethen and Embry, for example, Spectra and Pseudo Spectra, it's a beautiful book with plenty of phenomena in it and so on. And I want to mention one more such phenomenon, which is of interest. So what do we see on this first page? Let me explain a little bit. I'm looking at a large n by n matrix. Here, n is something like 1,000. And these are the eigenvalues of my matrix moving here. So I need to put some dynamics on my matrix itself. So I have a matrix, I add some noise. What is the most natural way to add some noise is to put Brownian motion on each entry. So that's what I do. It's very simple. I take my n, each one is an independent Brownian motion in the entries. But don't even think about a Brownian motion. You can add some small tiny Gaussians. There are many ways to do that. The phenomena I'm introducing, I think, are universal. And here's how the eigenvalues move. And something quite interesting raises a question here. They basically don't move at the edge, at least not on the same time scale. They move extremely fast in the bulk of the spectrum in comparison. Sometimes they tend to oscillate and have some kind of pairing with other eigenvalues, and they seem to gain by 2 or 3 of them. I mean, there are some interesting phenomena going on here that we don't fully understand, but I will explain what we do understand. This here is basically at the heart of this phenomenon is so-called covariance of linear statistics of these eigenvalues. Basically, you take a function, an arbitrary, nice, smooth, compactly supported function, and you look at the sum of f of the eigenvalues, or the trace of f of the matrix, if you prefer. And you wonder, what is a typical distribution? Is it Gaussian? What is the variance as the dimension of the matrix grows? And that's for the statics. If I add the dynamics viewpoint, then I have potential correlations between space and time encoded through these linear eigenvalue statistics. So we will discuss these kinds of things. And we will explain how that really enlightens these dynamics here.
And in particular, the central object will be the eigenvector overlaps. So I want to introduce that object first. In terms of statics, the random matrix I consider is, because I'm just interested in new phenomena here, I take the simplest possible random matrix. Independent, complex Gaussians as the entries. Nothing else, no signal, pure noise. This being said, when you have signal plus noise, it has been proved that some of the statistics I mentioned now still appear. What is known about the spectral measure of the eigenvalues is that it goes to the uniform measure on a disk. So my scaling, not my scaling here, I take my noise of each individual entry to be with variance of order 1 over the dimension of the matrix. That's actually the good scaling, so that there's a limiting spectral distribution. And here's a typical spectrum of my 5000 by 5000 Genebra matrix, independent complex Gaussian entries. And this is what I would get if I took 5000 independent points uniformly distributed on the circle, on the disk. So you see that there is a discrepancy incredibly smaller in the Genebra case. And we want to come to understand that, including from a dynamics viewpoint. In the previous movie, you may have seen that quite often these eigenvalues tend to repel each other, the dynamics way, and that's coherent with what we are seeing here. What are the overlaps of eigenvectors? That's the central object. We don't see that by looking just at the eigenvalues. What we need to look at is basically start with this formula, OII. So that's for the eigenvalue number that I label I. You look at a small perturbation of your initial matrix G. That's a deterministic statement here. You have a deterministic matrix G, perturb it by a little bit along some direction of another matrix. And you look at how much lambda I deviates from M0. Good scaling is 1 over T, if you believe in perturbation theory.
Is Frankie leaving for like or is he coming back?
You take the supremum over all perturbations. So that quantifies how unstable this eigenvalue is. How much
Watching a seminar right now, which I am.
That's basically
Don't want to miss.
Overlap. And some
It's
people
currently
call it also condition number.
in my building.
The condition number of
like
a
15
matrix
minutes to get there,
has-
so.
can be naming two things.
Portions of
Sometimes it's a spectral radius versus a small singular value divided by the small singular value. And sometimes it's individual conditional numbers for, it's not an object for the full matrix, but for individual eigenvalues. These are related, in fact. If you're interested in specific behavior of some eigenvalues, the OII is the important thing. What can be proved just by elementary spectral decomposition, that this OII is equal to this OIJ when I equal J, which is the dot product between my right eigenvectors.
Especially when I'm
So for I equal J, that's my L2 norm of my right eigenvector times the L2 norm of the left eigenvector.
The worst is
Of course, you have some
That's when these are-
scaling
they also
choice to
like-
be made,
yeah.
but the normalization is that Li and Rj
They stay
by orthonormal basis.
But the direct these are speaking.
So if you do this normalization with the right and left eigenvectors, remember we are in a non-Hermitian setting, then this instability is quantified in terms of zero corresponding eigenvectors in these values. It's interesting.
Hello.
Thanks, Frankie.
And this OII and OIJ also appears naturally if you do the dynamics that I mentioned. Because of course, imagine, I mean, it's this dynamics, like I put some noise in all of my matrix entries. So the instability of my eigenvalue should enter into the dynamics of the eigenvalues. So, in terms of stochastic differential equation, here is exactly what it is. You take, I would say, Orshanian process, just because I want to see but think about
I
language.
think I think about this. We were walking back. I think he was
For my matrix entries, that's what I mean. Then here is how the eigenvalues move. It looks like they move in an autonomous way. Basically, you keep the Orshanian vector for your eigenvalues.
But a lot
You
of
have a
like,
martingale
like,
term here. It's not a pure Brownian.
a
It's a
framework,
martingale term,
but not like
which has a
explicit,
complicated
this is
structure.
what that would look like. Person,
In fact,
and like
the
I think that's where those
instantaneous
are.
quadratic variations
But
between
also-
martingale terms associated to different eigenvalues is given by this OIJ that I described before. What does that mean? It means that if you have a non-Hermitian matrix and you add some noise, the eigenvalues are going to move, but in a way which is non-autonomous. It depends on the eigenvectors. That's very different from what you have for the Hermitian setting. If you have a Hermitian matrix, self-adjoint, any self-adjoint operator, that's true. You add some noise, then the eigenvalues evolve through some dynamics which can be purely described in terms of their own positions. There is no information encoded in the eigenvectors because of some kind of rotational invariance. That's something that can be proven. And then it's the famous Dyson-Brown that pops up. So I just wanted to mention the phenomenology in the non-Hermitian setting and the perturbations is completely different from everything we know in the Hermitian setting. For example, if you remember, I told you that the spectra is very well spread out. There is a small discrepancy. So some kind of repulsion between eigenvalues. Here's a repulsion, you can see it in the dynamics way. If lambda k is very close to lambda j, then instantaneously this drift term takes it far away from lambda j. But here you don't see it at all. Except if you really understand the statistics of the OIJs. That's one possible motivation for these statistics. I didn't mention, but there are plenty of motivations for studying non-Hermitian ensembles, including starting with the work, for example, of Robert May on dynamical systems for ecology, the spectral radius of some non-Hermitian matrices enters into the description of the dynamics. And there are many, many more examples. In fact, strangely enough, even in quantum mechanics now, there are some settings where you have external bath and so on, where non-Hermitian operators. And I must say that one of the main architects of new statistical studies of non-Hermitian matrices has been Jan Fyodorov, who is himself a mathematical physicist from the quantum project. Okay, so what do we know about the diagonal overlaps? If I give you a matrix, I give you an eigenvalue. Okay, the actual instability depends on the full details of the matrix, which is simple. What if I make my ensemble random? How unstable is the eigenvalue typically? That's a question. This question started to be studied, so really the random instability, by Schocker and Melick. These are physicists who could calculate the expectation of this instability. So this expectation of 011, which described, as I told you, basically the pseudo spectrum locally. Here is what they proved. They proved, so you see, you have eigenvalues, but they don't encode the full matrix, obviously. So you can condition on the eigenvalues to be somewhere for the Geneva ensemble. And then you have extra randomness in the eigenvectors. So, but if you condition on the eigenvalues, the expectation of 011 is a function of the eigenvalues that I call the i's. And it's kind of simple looking expression. The i's are the eigenvalues. The 1 is the 1 associated, it's for 011. It's the product of 1 plus the distance square, inverse distance square between the eigenvalues. Good formula. Now that's formula when you condition. If you uncondition, now if you may also integrate on the eigenvalues themselves, meaning you fix the 1, but all of the other ones are random. Then basically this you can do a mean field approximation. This should be basically just like if the zi's were distributed uniform on the disk. And what you end up with is this very nice formula in my view, which is when you have an eigenvalue somewhere at z, you expect the instability of this eigenvalue to be a multiple of the dimension, which is much bigger than in the Hermitian setting.
Dimension setting is 1, or 1 is 1, always. Here it could be of order capital N. Non-dimension spectra, of course, we have all seen this, some papers, maybe like Tau and so on, where we know they can be very unstable. But what this tells you is that they typically are very unstable. So they are of order N, but they are also much smaller when the eigenvalues is close to the edge. And that's exactly what was in this movie. They don't move close to the edge. Okay. It's really in this formula. Yeah, I mean, we can go back there. It's very clear. In fact, if you look at the instantaneous quadratic variation of any of these things oscillating, you will find that it's of order 1 minus the distance to the edge. It's proportional to the distance to the edge. And I think people are on their way to prove that it's true for any non-dimension matrix of the following type. You take a deterministic matrix plus noise, then you may not have a disk as a droplet. You could have, I don't know, whatever, a peanut or whatever. But still, the eigenvalues are going to be much more stable at the edge, always. It's a fun fact for which we have calculations explaining that, but we don't have a first principle explanation. We don't have something as simple as when von Neumann, for example, told us that eigenvalues of Hermitian matrices repel each other. Von Neumann had a very easy argument, which was that the codimension of eigenvalues of matrices with non-simple eigenvalues is not 1 but 2 as a manifold, and it's easy to understand. So there was a repercussion. But here, I would love to have such an explanation. Like, yeah, when you're at the edge, you have to be much more stable. I don't have that. Are there any questions about these things so far? No.
A quick question, maybe I probably missed it, but you said that you obtain this expression by integrating the above one over the distribution of the eigenvalues, which are uniform over the disk, right?
That's right.
But you integrate over the joint distribution of all eigenvalues.
That's true. It's not an easy calculation.
Yeah, you have dependence, right?
They are very strongly correlated. In fact, for a Geneva random matrix, we know that the eigenvalues have the following joint distribution. There's an interaction term here representing this repulsion. So you have to fix one of them and integrate over all of the others. Not easy, but that could be done.
The expression is so simple. I thought.
Yeah. It's not an equality as you see. It's as n grows, it really grows like this. In fact, I think what is more surprising is that we can know much more than the expectation. We know the full distribution of this overlap. So that's what I did actually a while ago, and I gave a talk about this in the math department about 6 years ago, I remember, with Guillaume Dubac, but then there were some extensions of this story, so I wanted to make a recap on the full, what happens in the past decade about this. So what we proved around 2018, 2019 was that in fact, this expectation can be upgraded to a full convergence in distribution. O11 we know is of order n times 1 minus the distance square. But then there is something as a multiplicative factor, which is random, a random variable of order 1. In fact, it's a very simple one. It's the inverse of a gamma distribution with parameter 2, whatever. So what is this gamma distribution? It has density t exponential minus t. Very simple random variable. Okay. You take the inverse of it. That's exactly the limiting overlap distribution. That's quite interesting for what reason? So look at this distribution of a gamma random variable t exponential minus t. When t is close to 0, it goes, it's like t. So when you take the inverse, in fact, it has a pretty fat tail. There is a probability that the inverse is very large, which is quite important. So the distribution of this instability has a very fat tail. So in fact, not only it's order n, but quite a few of them will be of a much larger order.
And in fact, we can prove that some of them are of order, I think, n to the 3 half. This kind of results has been proved simultaneously with Jan Fyodorov, whom I mentioned before. So we discussed this result with Jan, and then he came with another method to prove it. Our proof is very much probabilistic, and he came from he gave a proof based on a supersymmetric integration. That's a method coming from physics, but completely rigorous in that setting. And what is surprising is that the result is so simple with complicated proofs. So maybe there is a better understanding. So that's basically what I mentioned here. Jan's proof, in fact, extends also to the real Gini-Braun ensemble. Instead of having complex Gaussian as an entry, you can put real Gaussians. And if you have real Gaussians, now it's a real matrix. So the spectrum is symmetric with respect to the real axis. But you can still calculate things, especially on the real axis, you could calculate. Guillaume Dubac, after we did this, could make some extensions to way more ensembles, like also quaternionic Gini-Braun ensemble. It's not the most popular ensemble, but it has very nice structures. And this heavy tail that I mentioned, in fact, it was really predicted by physicists. And it was predicted based on 2x2 and 3x3 matrices. It kind of mirrors what Wigner did for repression between eigenvalues. He took a 2x2 matrix Hermitian and calculated was the distribution of the gap. And he saw some exponents for the repulsion and so on. And so, okay, maybe in the large n, as n goes to infinity, the same kind of qualitative behavior should remain. He also did that. And here, that was exactly what these physicists did. They could guess the heavy tail exponent. And after we did this, there was a lot of wonderful activity. So part of the activity has been to prove that for a matrix which has non-Gaussian entries but random ones, you have the same distribution. Universality. Another part of the activity was for matrices with much more structure, for example, signal plus noise. You may not, I don't think we have a proof right now of the distribution, but we have proofs of the order of magnitude of the neurons, that they are order n, typically. And the first line of research that I mentioned has been really on the impulse of Mohammed Osman with a young postdoc in London, and got wonderful methods for this. And there was nice papers also by Cipolloni, Schroeder, and Erdős at IST in about going the order of magnitude that we have. So this is an interesting story because usually between the integrability and the universality, there is quite a few decays in probability. There are quite a few decays. But here, only after a few years, the tools were somehow there to prove it's very robust. So as a proof, visual one of this universality, I think here, I forgot which one is it, but I made the histogram for a 5,000 by 5,000 matrix of these overlaps after normalization by 1 minus z squared. So we get something like that. This matches very well this inverse gamma 2. But you can do a Gaussian ensemble or an ensemble with discrete Gaussian, discrete complex entries. And you, in the large limit of dimension, you get the same thing. Okay. Any questions? Yes. So this is for the diagonal overlaps. You look at one eigenvalue. You wonder how unstable is it. Okay, but remember there is also this OIJ of diagonal overlaps, which is defined purely in terms of eigenvectors right and left. It's Ri Rj times Li Lj. And for these ones, we can also calculate not the full distribution. In fact, that's still open. There is not even conjecture about the distribution. But we can calculate the covariance. In particular, we can say if one eigenvalue is very unstable here, how does it correlate to another one being super unstable? And so that's what I just said is this formula. That's the expectation for 1, 1, and 2, 2. So this W is basically the distance between the corresponding eigenvalues, but we scale by the square root n, because the intraparticle distance in my scaling is typically 1 over square root n. So that's a formula which holds even in the so-called microscopic scaling when your eigenvalues are at distance for the microscope. That's what you observe. Okay, I don't want to enter into the details of what that means. What is really still a surprise to me is that this can be calculated. Meaning, going back to your remark, now you need to have a formula to start with, conditional on all eigenvalues, and then you need to integrate over all eigenvalues except 2 now. And it's still doable. The reason why it's so hard to get the full distribution is that, in fact, the larger moments are not defined. Because remember, it's a Hidden-tail distribution. So covariance is the best we can do. So identifying the distribution is really tricky. As this is an applied math seminar, if I go back to the Embry-Trefethen book and all of the motivations and so on, a key notion, as you know, is a pseudospectrum when you have a non-emission matrix. So basically what the pseudospectrum is when you have your eigenvalue of a non-emission matrix, morally speaking, what to expect is that if you pick a point Z, which is far from all of the other eigenvalues, Z minus your matrix should be possible to invert with a reasonable norm, not too large. But when you get close, there's obviously a blowout problem. But if you want to quantify that, what are exactly the zones where you have a bad blowout? It's not just about being close or far from the eigenvalues, it's more than that. It also depends on these overlaps around these eigenvalues. So in particular, this so-called pseudospectrum at resolution epsilon, what the previous result that I mentioned can prove is that with very large probability, if you pick a random matrix, the volume of the pseudospectrum is almost deterministic. You have a concentration in spectrum. So basically, that's the 2D Lebesgue measure of my pseudospectrum on a domain B, which is arbitrary. Basically, what you do is you have around each eigenvalue, you have a bit of a shape, and sigma epsilon is the union of these shapes when epsilon is very small. Okay. And now, if I take B, which is a box, for example, this, and I calculate what is the volume of my pseudospectrum on this domain. When for large dimensional matrix, it's basically universal. It's basically a deterministic, that's what it says here. So pseudospectrum volume is just the integral on the domain that I consider of this 1 minus z squared. And again, I believe this kind of concentration of the volume of pseudospectrum should be universal.
What's the C here? The small c?
Small constant it means for any small constant, this is 1. It's a limit. So it gets concentrated around 1. Yeah. Thank you. There is another consequence which I can explain better going back to the movie. Now, try to keep one of these eigenvalues, try to trace the trajectory of one of them. It's not easy. If you wait long enough, you may expect it looks like a Brownian motion in the plane. It does, but it does. We cannot prove the full picture, but we can prove the scaling at least. So more precisely, And I think again that's true for any reasonable non-emission random matrix. You have a deterministic shape, you add some noise, you get a domain, but then you perturb, you trace one eigenvalue, which will be like Grange. The conjecture would be that after some rescaling, so you look at between time 0 and 1 to rescale for a given t lambda I at some time ts, known as the initial point, divided by this. As t goes to infinity, that should go to Grange.
Some kind of a bit like a dense curve theorem, like the random walk converging.
Here's the random eigenvalue really converging. So that's a question still. What we can prove is the scale, is the actual exponent. What we can prove is that after time t, my lambda 1 of t has in fact moved of order square root t, that's a square. And it has moved faster if you are far from the edge. I'm not sure how I'm doing with time.
There are 30 minutes. Yeah.
Okay, it's couple of thoughts, that's perfect. So here, what I told you is the story is really you have a non-dimensional operator, you perturb, you want to understand behavior of eigenvalues, everything you can. And we saw it's encoded these dynamics by these overlaps. And in particular, what I find to be intellectually satisfying is that you can understand the correlation. If you have a very unstable one, yeah, in fact, it's more likely to be unstable for the ones around it. And you can quantify it that way. Now you can ask even maybe more maybe a natural question, but I think still important for some topics, which is, okay, if you have an eigenvalue which has some instability and you add some noise, you can ask about the instability of the other one, but not at the same time. Okay, how do they correlate? So it's now about space-time fluctuation field. And that's what I've been doing last year with Giorgio Cipolloni and Jiayong Wang. To describe this story, I have to take one step back and explain a little bit what the general series of fluctuations for random matrices. Basically, the story is as follows. If you have emission matrices and you want to understand how the spectrum ripple, you can take linear statistics and prove the variance is very small. That's dimension 1, and there is an infinite number of models in the self-adjoint class that has been studied for which this phenomenon has been exhibited. Dimension 2, there are already quite less models. How do you do the dimension 2 in random matrix? There are two ways, I would say. One is just to have a non-emission spectrum. The other one is to have a non-emission 1, but dynamics. And in fact, you can prove that you have the same type of repulsion in both cases, I will explain. But this work from last year is about dimension 3. We have a dimension 2 non-emission matrix for which we add the noise parameter, the time parameter. And then we get a 3D Gaussian field with an explicit covariance, which will be related to this story about overlaps. So that's the plan for the second part of the talk. But for those of you who don't necessarily know that story, here's what is known in dimension 1 in one slide, but there are many declinations of this. The easiest model in random matrix theory is always random unitary matrices. The eigenvalues are on the circle, they have some symmetries, integration formulas are nice, it's better than any other model. So let's talk about this one. So you take a Haar measure on this unitary matrix, uniform measure on the orthogonal basis. The thetas are the eigenangles. And you look at linear statistics for a nice function f. I don't care about regularity, smooth, whatever. For the theta case, and the same for some other test function g. And you wonder when the dimension is very large, what is the variance of the guys? What is the covariance between them? In fact, what is proved is that these converge each one of them converge to a Gaussian random variable after the recentering with no normalization. You don't need a central limit theorem type of normalization. No need for a 1 over square root n here. And that's really a consequence of repulsion. Non-obvious. In particular, if you don't have a normalization, you may not expect a Gaussian. But you do have a Gaussian and you don't have normalization. That's quite interesting. And also, if you look at the covariance or the variance of these limiting Gaussians, that's here and there. It has the following form. It's a double integral of f prime g prime with the log of the distance between the evaluation points. So this is what we call a logarithmically correlated field. You may have heard this expression, log correlated field. What are log correlated fields? These are random processes. I mean, these are processes for which randomness occurs at all scales. Scales meaning distance scales, like powers of 10. At 10 to the minus 10, between 10 to the minus 10 and 10 to the minus 11, you have some randomness which is due to that scale of order 1. And the same between 10 to the minus 3 and 10 to the minus 2, order 1 also. So anytime you have a scale invariant type of problem, you expect these log correlated fields. And that has been known since Freeman-Dyson, basically, the paper with Mehta in 1963. And then people have extended these results to an infinite number of models. I told you I don't want to go too much into this, but more interestingly, I want to go to dimension 2 and 3. So for dimension 2, as I told you, there is one way to do that, which is space-time, but I don't want to enter into that too much. I will focus on dimension 2, the Gini-Murray ensemble that we discussed. The Gini-Murray ensemble, remember, you just have a disk and many eigenvalues at once. And this is the joint distribution I wrote on the board for the eigenvalues. And you wonder this, just the same question. You take the trace of a function, a nice function of G. Take your function to be simple, take it to be supported on the disk. Okay, so supported strictly on the disk. There are some boundary effects I don't want to mention for now. Take it supported on the disk. Same for G. And again, you don't need a normalization. It's a remarkable fact due to repulsion, and you have a Gaussian in the limit. Central limit theorem with no normalization, if you want. What is the limiting variance? It's given by the Gaussian free field in dimension 2. Beautiful object. It's basically the equivalent of what Brown motion is. Brown motion is a universal object in dimension 1, the most universal one, I would say, in dimension 1. And Gaussian free field is probably the most universal one in dimension 2. It's characterized by this fact. For each test function f and test function g, f is a random variable and g is also a random variable, Gaussian type, with covariance given by the Dirichlet form, gradient f dot gradient g. Okay. And there are many ways to write this. If you do some integration by parts, you can replace this single integral into a double one, just because the Laplacian is the inverse of the log convolution operator in dimension 2. So here you recognize it's a log correlated field again. There is a boundary term. I don't want to enter into this for now. And there have been some extensions of this result, which is due to Ryder and Verhaeghe in 2007. And it really tells you that from one of the most basic objects, linear algebra, just a big matrix, the typical big matrix, you have the Gaussian field. It's a beautiful fact. Questions about this result? It's one of my favorites in parametrics here. Now we want to understand the same when we do some dynamics. I'm not really mentioning the proofs. The proof is relying on some integrability property of this ensemble. Basically, it's called a determinant point process. Because here you recognize the van der Waals determinant square.
then it has a specific algebraic structure which allows a lot of analysis. Now, what I want to explain in this slide is that what we want to do is now to understand this field, how it evolves with time now. For the static field, as an object depending on time, what is it?
So I'm looking at the dynamics for which the Gini ensemble is equilibrium. Just Orsheidenbeck on the space of matrices, if you want. I told you already that the eigenvalues that I denote sigma I here are given by a martingale term and this attracting term, Orsheidenbeck type, and the martingales are correlated now. It's not a autonomous evolution. This is just something I already wrote here. The overlaps at time t for the matrix enter into the instantaneous quadratic variation of my martingales. So understanding these overlaps better can enlighten us about the dynamics. Or reciprocally, if we have another way to understand the dynamics, then we can maybe infer some information about statistics of these overlaps. In fact, we will take the second view. So here is the result. Exactly kind of mirroring what Ryder and Virac did. I'm looking at linear statistics of the Gini matrix, but at some time s, if it was just one time s, it's equilibrium, so it's a Gini matrix, but also at some time t. Now I'm looking, so I know each one of them will converge to a Gaussian with covariance this Dirichlet linearly. But now I want to understand the covariance. How does it depend on time and so on. So what we end up with is a formula which is exactly the same as Ryder Virac, except that instead of having the log of the distance here, we have a kernel which is a bit more complicated. It really does depend on this gap in time. So this kernel, it should coincide with theirs when s equals t, obviously. So s equals t, that's tau equals 0 here. So it means that this prefactor is 0. And then this is 0. This is 1. So it's the log of the distance squared between the NW. So it's exactly that formula. It's not obvious, but of course you expect this K to be a symmetric in the NW because you're at equilibrium and it's a reversible dynamics. It's not obvious when you see this formula that it's symmetric in the NW. It doesn't look so, but if you do a bit of algebra, it is.
Yeah, that's like the wrong motion after time t and after s.
Yeah, that's right. GT and GS, I should have changed that. It's actually X. No, sorry, it's X. Thank you. Okay, so now this is my context slide. So how does this result relate to general theory of fluctuation fields? So it is, as I told you, in the family of log-correlated fields. Dimension 1, we have the log of the distance between the NW. Dimension 2, it was also, again, the log of the distance. Here, it's what you can find is that as Z is very close to W, this K behaves like the log of the distance between the point Z at time S and W at time T. But this distance is not the Euclidean distance in R3. It's a parabolic distance. Okay, there's a square here, but an exponent 1 here. That's typically diffusive. So what is exhibited here is a 3D log-correlated field, but for the parabolic. And this object actually have appeared in many contexts. Not exactly this K, but the singular behavior of this K is in the so-called Edwards-Wilkinson universality class. It has appeared for probably the most natural thing is when you take a stochastic heat equation in dimension 2. Imagine you just take the heat equation in dimension 2 first, but you add a space-time Wine noise. Okay, so you have on the one hand the spreading behavior to Laplacian, but you also have the space-time Wine noise, so there is a fluctuation. In the very long time behavior, gives you a Gaussian process on the plane. It's actually a Gaussian distribution. It's not defined pointwise. So you need some smoothness functions to integrate it with, but and it has exactly this singular behavior. Okay, so that's the Edwards-Wilkinson neurochain class. Basically, when you have dimension 2 and noise fluctuation fields, Edwards-Wilkinson is a safe bet about what will be the fluctuating field. So there are plenty of references here for anyone interested, but I will not get into these details. Questions? So here I mentioned what this theorem. So here in this theorem here, I took my test functions f and g to be macroscopic. I took them to be, on domain of size 1 inside here. I could take them to be supported on a smaller domain so that I understand better the local properties. If you do this the zooming procedure, what you obtain is really the log of the parabolic distance, but it is weighted by a factor which is proportional to the distance to the edge, just like for the overlaps. What it really means is that there is less fluctuations associated with time when you are close to the edge. Okay, so it's coherent with our previous studies. And in fact, it's again 1 minus the distance squared. So that's basically the only thing I think to be remembered maybe about this. Now, I didn't tell you about what happens at the edge. Exactly. Yes.
Actually, from the previous slide. Can I go back to the previous slide? Yeah, I want to ask about the answer here. The answer is a positive number, but can be something like we have some battery for that.
Can you repeat? Sorry.
I wonder about the size scale here and about minus answer.
Oh, and you mean this scale here?
Yeah. Do we have any condition for alpha, and that has to be greater?
Oh, alpha is between 0 and 1/2. Yeah.
0.
Thank you. So the so-called mesoscopic is anything between microscopic and macroscopic. And yeah, I should have mentioned that. So alpha is any number between 0 and 1/2. Alpha equal 1/2 is forbidden because you start to see the very, very fine details of the microscopic behavior at alpha equal 1/2.
So it's not go to somewhere like has to be. It cannot go somewhere. It's greater than 0, but not something like even like small. Like it's not something with the logarithm, right?
It could be, so alpha is really a fixed number that I take, it could be 0, that's my macroscopic case, but it has to be smaller than 1/2. Which should be the microscopic. Okay. So what it really means, if it's a box, I pick a box, but I want the number of particles in that box to diverge. Yeah, to have some kind of large limit behavior. If I'm on the microscopic scale, they have a limiting behavior, but where the very fine details matter. Okay, I didn't mention much about what happens at the edge. So let me go back to Ryder and Virac. Here, that was a result when you have F and G, which are supported strictly inside the disk. Now, if they overlap the edge of the disk, and let's say that your function F is supported here and your function G is supported there. So the value of F outside of the disk should not matter much because anyway, there are no eigenvalues there. Inside we understand pretty well, but now how about exactly what is the limiting fluctuation field on the boundary? What kind of we understand a bit. So what Ryder and Virac proved, it's very interesting, is that basically if F and G overlap the boundary, to this covariance, you need to add one term. And this term is as follows. You look at the restriction of your function F to this arc, same for G. You call them this German F or German G. And then it's integral of f prime g prime log of the distance. So it's exactly the same thing as what we had for unitary ensemble by Dyson and Meta. It's kind of strange. So you start with this 2D, and it looks like the limiting field is a superposition of two things, which would be what you would get if you had a gas confined to the circle, plus this Gaussian free field. Okay, there is, as far as I know, there is no conceptual explanation for that. Calculate on both sides and you get the same result. What we proved is that this analogy remains in the dynamics. In fact, we can look at the fluctuation field at the edge. Compared to what I told you before, I need to add a term. This P is a Poisson kernel. So if you have a function on the circle, the Poisson kernel is basically, yeah, it's defined here. Basically, it dumps the high frequency Fourier coefficients exponentially. That's your Poisson kernel. And basically, it's you have an extra term at the edge, which is exactly the same as what you would have for unitary dynamics of particles confined to the circle. So even at the dynamics perspective, this superposition coincidence survives. That was a surprise to us. No conceptual explanation. So what this graph is, what this picture is these particles confined to a circle. This is time, and your particles are repelling each other and moving up. So they move on the cylinder. This is exactly the drawing of taking n Brownian motions on the circle, but you condition them not to intersect. It happens to be the same dynamics as Langevin for the equilibrium of unitary group. It's not obvious. That's what it is. And this, for finite n, we don't have this picture. In particular, the eigenvalues which really are at the edge, it's rare, but they may not be confined to the edge. Sometimes they will go back into the bulk. So they really are, for finite n, they are not confined. However, for large n limits, the fields coincide. Maybe it's this I will say. There is a nice understanding of our covariance structure by stereographic projection. I will not go too much into that because what I do want to explain is to go back to overlap story. Now that we have this result about space-time correlations between test functions for these non-dimensional vectors, how do we understand, can we infer some information about overlaps between different times? So that's this formula. In fact, we can prove this, that, so forget the details, but if you pick an eigenvalue here called sigma I, but at some time s, and another something called sigma j at another time p, and you wonder how do the eigenvector overlaps, how do their instabilities relate? Well, in the sense of the covariance, they relate by the quartic distance, meaning that where the distance is against the parabolic distance. So you have the distance in space square plus the difference of time, and a prefactor, which is the usual 1 minus v squared. And then you take the square, so it's quartic decay of correlations. So if you have a matrix and you observe, okay, here is a condition number here, it's n to some power, and it's very likely to get an instability far or whatever. I mean, I expect that this will occur in periodic. That's coherent with what the result with Guillaume from a few years ago gave, which was again quartic distance, but purely in space. If S equals T, that's basically. I want to explain just to give a sense of one line of proof. If I give you the result on fluctuations of linear statistics, how do I obtain this about overlaps? Very simple proof that I want to explain. It's this one, or not? This one. It's this one. Okay, so what is this result that we have by other means that I didn't tell you? But we have the covariance between linear statistics at some different times. It's a formula is here. Now, if I apply the Ito formula, for example, S is smaller than T, and I apply Ito in T. So I do dt of this guy. I apply my Ito formula. I know that the eigenvalues are satisfying these diffusions guided by overlaps. So in fact, the OII appear in the covariance and I take my G. That's what I get. But here I need to differentiate in T. So I differentiate my log, I get the inverse. Okay, so I do Ito, that's what I get. Now trick, reversibility. I'm looking only at my dynamics at equilibrium, so it is reversible. So I can exchange the role of S and T. I just do that from here to there. But now that I have exchanged my role of S and T, and S was smaller than T, I can do the same procedure, but now differentiating in T here. So I differentiate again, once more here, I get quartic. And here I differentiate, I get another set of overlaps. And because my test functions f and g are arbitrary, I get the covariance in the distributional sense. Okay. So it's a bit of reverse engineering we are doing here. We have another way to understand the projection fields of one-dimensional matrix. We infer some stuff about the eigenvector overlaps. It would be nice to have a better direct understanding of eigenvector overlaps in a geometric manner or whatever, but these are very complicated objects. You have the right and left eigenvectors normalized, you take the dot products, apply. But they encode everything. You don't need more to understand the stability and so on of the spectrum. So here we find some new statistics or covariances by another way, which is related to the dynamics of the Gaussian free field, basically. Okay. Thank you.
So do we have similar result for the real scale, or we just have this?
Or real genome?
Yeah.
Yeah. So we can develop a similar picture. It could be done, and part of this program has been done. But there are differences, of course. You have now your spectrum is symmetric. So this symmetry property survives in the art and limits. So you don't have a Gaussian free field here. What you really have is a Gaussian free field plus it's symmetric, and you get something symmetric like this. And for the overlaps, what happens is that if you look locally for the real Geneva ensemble far from the real line, what you really observe is something similar to the complex Geneva ensemble. Everything behaves the same. The real difference is when you are close to the real axis. Then the symmetry kicks in and changes the statistics. But this is understood, yes. Especially thanks to Jan Fedorov.
Whenever in the real case, the eigenvalues can be very close, right?
You are worried that they could get very close.
Like, for example, I see the picture here when you have the line of the direction is kind of what that is cannot cross each other, right? But I worry on the real case when I see maybe the line can cross each other.
So in the real case around here, there are some great phenomena. In fact, some of these eigenvalues will be exactly real. But this number of real eigenvalues is not deterministic. It's a random number. So what does that mean from a dynamics perspective? Let me zoom in. It means that what happens from time to time is that you will have a pair of symmetric eigenvalues which will collide and create a pair of real eigenvalues. And reciprocally. So it's a fun phenomenon to see actually in simulations. You have this eigenvalue bouncing this way. So that's related, in fact, to some challenges, but from the overlaps viewpoint, things can still be understood, in fact, thanks to the supersymmetry methods that Jan Fedorov has developed.
So because what we are doing here, we are doing that for when the own eigenvalue are different, right? Like lambda one greater than lambda two and so on and so forth. I wonder in the general case where they have the Jordan decomposition, that we have the Jordan block, that you can have not only the eigenvector with the same eigenvalue, you also have the eigenvector. You don't have eigenvector, you have the zero lines eigenvector, right? So
Do I understand correctly that you want to have nilpotent blocks?
What?
You want to have nilpotent blocks in your journal
Yeah.
decomposition? Okay. So what is known is that if you start with a matrix which has some nilpotent blocks and you add some noise, and of course initially eigenvalues will be incredibly unstable, infinitely unstable if you want. But if you add a noise which is not exponentially small in its dimension, but let's say even polynomially small, like n to the minus 10 in the dimension, that will be enough to completely destroy the nilpotent structure and to have something which is much more stable than the nilpotent setting, but still much less stable than the Hermitian setting. So you should think about nilpotent as a complete pathological setting of instability. And here we are more looking at the typical instability of the non-Hermitian setting. But in fact, it's really typical in the sense that even if you add a very small noise, polynomially small, to an nilpotent, it's enough.
And when you add a noise, it's already making the eigenvalues become separated.
That's right.
No more question. Let's thank our speaker again. Thanks.
It was fine, not very light, but
It's good.
no,